Correct. Here?
Yeah, we can.
A few minutes more there, right? Or slightly over. Huh? It's okay, I can wait. Yeah, so good. Looks like a class. This after a long time. No trips. Don't know why. Yeah. Okay, thank you. We must acknowledge my discussion, a lot of discussion with Professor JS and all my students. Actually, the discussion with him being good this particular steps. I remember that 2 weeks ago, you also mentioned about the biennial oscillation, isn't it? That time only I thought that maybe I just thought about biennial oscillation. It's one of the most this one. So I'll try to finish in half an hour. So in 1987, June to September, there was a strong El Nino. This is the SST picture of 1987 system. Strong El Nino. In fact, actually, it was I think it was a decaying El Nino in JJs. It already picked up, and then by the next winter, it was kind of a La Nina, and then next year, 1988, was a La Nina. Okay. And then what happened is this one. Yeah. So if you look at the CFSB2 forecast of 1987, this is the ensemble mean forecast of CFSB2 of several members, about say 30, 40 members of CFSB2. And so it gave predicted lower than normal rainfall over India, as well as over maritime continents. And over the central equatorial Indian Ocean, it gave a predicted positive rainfall. Okay. The right hand side, I give you the estimated GPCP, that's basically observation-based estimates, like some satellite and we get and their rain gauges possibility. So it came out to be right, almost right. To some extent, it is right, apart from this location. So please note this location. Over India, at least it was right. Okay, even in the maritime continent. All right. So then, a decade later, in 1997, there was another strong, even stronger than that. In fact, it was kind of evolving, I believe. So in JJS, it was an Eastern Pacific El Nino, very strong. And it is a typical El Nino picture, El Nino pattern of SST, and with the negative PDO, positive PDO, and this one. Now, this particular year, when CFSB2 forecasted again lower than normal rainfall over India, in the maritime continent, and positive rainfall over central equatorial. Very, very similar picture to 1987. But what exactly actually happened is this dipole was almost right over Indian Ocean, but over India it was wrong, came out to be wrong. Look at the head bay of Bengal rainfall, it is much larger than the observation. Only a patch of South Central India was negative. Rest of them was normal or positive. So 1997 was about towards came kind of close to normal. It was not abnormal, but normal. Okay. So question comes that what went wrong in 1997? Then, in fact, former department professor Gadgil along with his colleagues have published a paper where they found that the equatorial Indian Ocean, this region, there is a dipole positive to negative, and the dipole gets connected to the Indian rainfall, and it was kind of instrumental in having this rainfall over a few years, like 1997. 1994 also was a very strong rainfall flood over India, but it was not explained by the AIMS. Okay, so this was here. However, if you look at the time series of Indian rainfall, last 122 years or more than that year, at March to this one, that whatever available instrumental data is available. There are several time scales involved here. Multi-decadal, even to biennial, okay, and all different time scales. So some of the major oscillations are not associated with many of the major oscillations. I'm not talking about this one. So this particular phenomena doesn't come as an oscillatory behavior, unfortunately, and also doesn't come during the beginning of the month. It usually comes at the August and September. Okay, that particular thing. So is there any oscillation? Is there any dominant mode apart from the EMSO mode that can be used to predict or understand the internal variation of the modes, right? So now this is again from 1971. I have plotted the observed rainfall, which is the bird ISMR, and filtered the data, which can be basically filtered using FFT, first harmony analysis, right? Filter the data, knowing that there are certain dominant modes of rainfall over India. All right. So this is that the blue line is the less than 3 years, basically 2 to 3 years. We can get 2 years, 2 to 3 years, and so on. This could be, you can think of this as the EMSO mode, and this is subdecadal to decadal. So apart from everything, look at, I mean, I'll not go to the details. I just want to point out 2023. The last bird is 2023. The first mode, that is that less than 2 year mode, which we usually call it 5 mode now in this particular figure. It was strongly negative. The last mode or the third mode here, whatever I have put here, that is decadal to decadal mode. Decadal, anything which is greater than 7 years. So that some of the 3 lines will give you the actual value. Okay. It was also negative, but the 3 to 7 year mode was positive. So now 3 to 7 year, we know very well gas associated to the EMSO. Correct? 3 to 7 years associated to the EMSO. But when you filter the data like that, you see a positive, what I should say is that the anomaly associated with this particular mode is positive. Ideally, it should be negative because in 2023, in JJS, there's a strong El Nino again. All right, strong El Nino again. So if this is an El Nino, it looks like now 1997 now, isn't it? Kind of El Nino. However, the rainfall was to some extent this one. But last year rainfall was below normal. It was not like 1997. So look at the moisture budget. So it is not just that statistic now to come to some sort of physics. We look at the moisture budget. So we have done some moisture budget analysis here. So all the positive values here are in the positive X and Y direction. So if 70 east is here, basically positive means more moisture coming towards the Indian region, and 90 east, more positive moisture is going out of the Indian region. And these birds are, blue is the La Nina and flood together, moisture budget and moisture plus anomaly. So what happens is, and during La Nina and flood, you get more positive here and less going out from this region because this is negative. So it can't see. So there's a convergence here. And El Nino droughts, you get more outward flux from this region. That is basically less comes in and more goes out because the mean is positive here, mean is positive here, and this is also mean is positive here. Also look at 7.5 knot, that is northward flux here. Also during El Nino droughts, it's basically sort of positive. So this cancels out. It's basically, therefore, you can think of at 70 east, or sorry, 70 east, whatever that flux goes in. If that decreases, then kind of there is an El Nino drought. All right. The green bar is now 2023 picture. And look at these two. Similar, and similar. So basically, from a moisture budget perspective at least, 2023 was a typical El Nino year. There was a drought, there was an El Nino, typical El Nino year, isn't it? So, but
2023 both might have higher.
No, this is correct. So, but these are what happening is that these are all composites of several years.
Okay.
So there are variations. So the mean goes somewhat. That's one. Okay. What I'm going to say is that on an average, the signs are very, very similar to the mean LD. So now if you just go back to this particular, go back to this particular picture. Now therefore, this particular filtering of the mode was not therefore not right. So what happens is when you have this filtering like that, we give a particular frequency band, and that is restricted by the frequencies given to which we will filter, right? But in actual nature, will not go through that particular frequency band oscillation, right? So what happens before in that particular oscillation will impact what is happening in the future. So possibly what is happening is that this for this particular case, so already some oscillations are present, and so this mode has to come to a positive sign to give you the correct time period which you are asking from them, right? So there is something is missing there. So then people go to come out of this problem, people go to something called empirical mode decomposition. So in that particular case, you give the data set to the to this particular. This is empirical. This is not based on any mathematical theory, but you kind of find out the envelope of the data successively, and until you find out the highest variance from the fact that the envelope gives you the fluctuations, very large fluctuations. Okay, there are details of that, but nevertheless, if you use that particular this one, you can get different intrinsic mode functions. Okay, and usually what happens is the first intrinsic mode function will give you the highest variance. So if I look at the same ISMR now from 1940 or so, from the 2022 or 23, 23 is there. So this is the ISMR is the gray bar, and IMF1, that is the first intrinsic mode function. It gives a very strong negative value here, and it was negative even last 3 years, even if the actual value was positive last few years. But last year it was a 2023 was a very strong. And this is the power spectral density of that particular IMF mode, which is the blue line, and the gray line is for the ISMR. So look at that. This all the variance is within 2 to 4 years, 2 to 3 basically, mostly 2 to 3 years, 2 to 3.5 years. Okay, there is a big variance in the 4 to more than 4 years here. This is the ISMR, which is greater than around 7 years. There is a variance mode, which is not picked up by this IMF1. Okay, the first. Now you take this orange line, remove from this actual line, right? You get a residue, and do the same method, apply the same method to the residue. So you get the second IMF. So this is here. So now you find that this already the time period is long for this particular case. All right. So now this is again ISMR. Look at that. So now this time period or this IMF picks up the 7 to 10 year mode, right? And then you repeat it, you keep on going, and you find out that it keeps on going to the larger modes, and then or larger time scale. So finally you get different modes. So what I do is that now take the first 5 modes of ISMR and do a power spectrum. Okay. So very clear that the first mode, which is the highest variance, which explains about 70%, I think I've written down there. So this is mostly here from 2 years to about 4 years, and even this particular case, this particular peak, which is supposed to be the ENSO peak, is here, right? The first mode. So now the disadvantage therefore of this IMF is now I cannot distinguish the biennial to the ENSO mode, right? Now, other case, there's another way of disadvantage. So everything you have to be very careful. Then IMF2 is here and blah blah blah, right? Now I show the same thing for 3.4 JJS SST, and again that there is a strong biennial mode here, and then they are 4 to 7 year mode here, and its IMFs, different IMFs shows the IMF picks up that, and there are decadal and subdecadal modes. So it looks like this 2 to 3 year or 2 to 3.5 year, whatever you call it, 2 year mode, which can be called as a quasi-biennial mode of the oscillation, is present very strongly in the Indian summer monsoon as well as the 3.4 SST, right? And we know that sometimes they are connected to some extent, possibly, and many times ENSO comes only from the pure ocean atmosphere coupling at that particular region, then maybe you may get that coupled with the ISM, right? So thus, what it suggests is that although there is a mode present here, similar mode, they could be very independent or to some extent dependent, right? Which is not very, we are not very, very clear. We are not very sure of that. It further gets complicated when you do the Indian rainfall in x-axis and the following winter's Australian rainfall. This is now JJ is starting here. Now upcoming that whatever is coming that December, January, February, if you take that particular year's JJ's Australian rainfall, you plot it here, you get a somewhat correlation 0.27. Moderate. But moment you take the first IMF of both the time series, as we showed that first IMF is mostly the quasi-biennial, all right. But including the ENSO, of course, the we should not forget that it increases substantially. Right? So basically suggests that Indian monsoon and Australian monsoon are connected. Like this Indian monsoon will follow by the same sign Australian monsoon in the upcoming season, right? And the next time Indian monsoon next year it kind of becomes negative. If it is positive here, next year become negative because biennial oscillation suggests that.
Yeah,
Positive.
all the statistical models that were running on others, they never use Australian rainfall. Did they use? They should have.
They don't, but they may use some parameter. If I remember, there are some parameters in the southern hemisphere, so that may be a signature of the Australian. But I'm not very
Directly, because you
sure.
know
Directly, you don't have.
why March, what the rainfall in Australia was.
Right.
If that is connected in 0.4 point,
Yeah.
it is as good as 3.4.
Right. Right. Yeah.
And it's not, you don't have to predict it.
But this is the Indian monsoon. So Indian monsoon, this Indian monsoon to the next Australian. So Australian monsoon we have a benefit from here. But I have not done. But if you include that, you are right. If you include now the biennial signal,
Indian monsoon follows Australian monsoon.
yeah, Australian monsoon follows. No, Australian monsoon follows.
Huh?
Australian monsoon follows. So the 24 Indian monsoon and 24-25 Australian monsoon.
Okay. Not the other way.
Not the other.
But I'm saying, we know this year's Australian monsoon is over Jan to March.
Yeah.
Would that help me to predict it?
Yeah, you can check that. Okay. So what it suggests is that this biennial oscillation possibly is a large scale phenomenon. It's not just localized to Indian region, isn't it? That's kind of it's kind of known. I'm just not telling anything new. It's just kind of known. Okay. So knowing that, people have tried to understand the theory of biennial oscillation. Okay. So there is a famous paper by Chang and Lee in 2000. They took 5 regions over the tropics and Indian Australian region. So this is the Indian region, and QI is the heating over the Indian region. So heating is a proxy of the rainfall. All right. This is equatorial Indian Ocean where you have QI, that is the zone wind, and the SHT, this is temperature. This is the West Pacific Ocean, same thing. This is Australian rainfall, and then this is the TE supposed to be the Eastern Pacific SHT, sea surface temperature. Okay, but they don't have explicitly this particular parameter. They don't. There's not a prognostic parameter. They just impose it, and then I think believe in the first model, they have just imposed it. Okay, then they have some sort of an evaluation of the evolution of that parameter, but not based on this particular model, based on some other. I think that's based on Keynes-Zodiac model. But anyway, that's not a big deal. So what they propose is, in the northern summit, if you have positive rainfall, for example, over the Indian region, that kind of gives you this gradient temperature here. So the winds become stronger. Wind becomes stronger here because that's like a Somali theater obviously becomes stronger. Now, this circulation becomes stronger also because this usually what will happen is that this is a La Nina, typical La Nina kind of picture. West rainfall over West Pacific Ocean will be larger. So this is also stronger. The water cycle is stronger. So this also will be stronger. All right. So usually winds are this way. That is the trade winds. This U1 gives you a weaker trade wind, and therefore will make this ocean make this region warmer, that western equatorial, sorry, western Pacific Ocean, and this wind will make this region colder. All right. Then this also again the same thing. Now this is apart from the fact that now they include the winter, northern winter, the next season. Then because of this warmer western Pacific Ocean, that gives more moisture flux, and this becomes stronger now, Australian monsoon. And that Australian monsoon stronger, including this particular a stronger Walker circulation, gives you a different east-west gradient of the SST, strong negative, but the Indian Ocean is already cold. So the next season, because of the cold Indian Ocean, the moisture, the amount of water vapor in the atmosphere is less, and thus even if the winds are about the same, but then the moisture flux becomes less, and then the next season, here the Indian rainfall becomes less than the normal. So now they have several parameters because they not only calculate rainfall, they also calculate the SSTs and winds. So rainfall SST means all the things they calculate in the parameter in the model, and they take a reasonable values of the different parameters. And given that, when they run the model, you look at this Indian rainfall or South Asian rainfall, they call it. This is June, July, a high rainfall, followed by a high rainfall in the Australia. Then next June, July is a negative rainfall, and then less rainfall here. So they get a beautiful diagonal signal just using a 5-box model. Okay, but please remember that this model was generated, or model was constructed, keeping in the mind that there is a biennial oscillation. All right, so they fix a parameter to such that it is the biennial oscillation comes. Okay. Now, if you come to the reality, this is the composite of SST anomaly starting from a flood here. Now, to start with Indian monsoon, if I started flood here, this is July SST anomalies, December SST anomalies following the flood, and then the May 1st SST anomaly. Please remember that in that particular model, their basis is that SSTs over the Western Pacific Ocean retains, with SSTs over the Western Pacific Ocean retains throughout the from summer to the next winter. Then only Australian monsoon will become stronger. And SST in the Indian Ocean becomes also retains from the summer to the next next summer, so that your next Indian monsoon will be weaker. All right. So now, if you look at this, there is hardly any signal of strong SST anomaly over Western Pacific Ocean. Flood here, neither for a drought here. In fact, I see a kind of a southern Indian Ocean dipole kind of picture here, rather than over Western Pacific Ocean. But for December it is here, but by the time next May comes, it is almost nothing the following week, right? Not just that, if you look at the correlation between the monthly mean SST and ISMR, and for the same year here and the following year, look at this Arabian Sea values. It is during June, July, August, there is hardly any correlation of the SST over Bay of Bengal and Arabian Sea to the seasonal mean says. It doesn't say that Indian Ocean, they do not impact. Okay, the interseasonal time scale, there is a lot of things to play. So we have to now think hardly that how the SST anomalies can persist a couple of seasons or from one year to next year. At the same time, to give you the biennial oscillation 1 year to the next year, there's a flip here. When this relationship itself is so low between the SST, local SST and this one. Then, if you look at even West African rainfall, even there is a power spectrum West African and the Indian rainfall. It also shows kind of a biennial signal. So I'm just trying to put forward that it is not just the Indian region or Australian region, even over West Africa, there is a signal in the biennial mode, right? So thinking therefore that people thought now differently, and recently, I think recently in the sense that few years ago now, a paper came. They try to prove now that the tropospheric biennial oscillation is indistinguishable from the white noise. All right. So what they now look at it. I think got to. Okay. So this is the definition of biennial signal. Biennial signal, what I'm saying is that a particular rainfall over a particular year should be higher than the previous year and the following year, or rainfall over a particular year should be less than the previous year or the next year. That's basically a biennial signal, right? Pure statistical biennial signal. So now, if you define that particular way, then if you think that if you write that rainfall over a particular year is K, right? Then this is a little statistics here, but I think I'll go very quickly. Then the probability of the rainfall will have, we define the probability that the rainfall will be K of that year I is given by a PDF K, right? Because what will be the value of K? If there is a PDF of K, the probability is that. Then this is nothing therefore that the probability that this biennial signal exists, that is that rainfall over this rainfall here, if you look at only the first condition here, only the first condition here. So this rainfall will be greater than this rainfall, can be just given by this particular function. Okay, this integral of this, so that basically CDF of K. And then for the other case also, for the third case, this also is a CDF K. So if you want the details of that, so together you know that DD of the CDF is basically the PDF. If you integrate that, you get that total probability of a biennial signal only for the one case, that is that this year's rainfall is larger than the previous and the next year, can just be given by this. But this is not, but here, so this is basically 1/3, right? Because this is this one. Now what happens is, now we have two things, biennial things, remember that. It has to be either this or that, right? So you have just proved one of those. If you take both of them, therefore the total probability becomes 2/3, because 1/3 plus 1/3, there's an addition of the probability, right? So it becomes 2/3. So basically 66.7% is the probability of a biennial signal just from the random noise. That's all. That's what they have done. Now they have taken several data sets, including CMIP5, CMIP6 models, and then rainfall data, model runs, everything. And basically what they are trying to say is that all the cases, there is hardly any signal above the 95% confidence interval of a white noise. Basically they are saying is that this particular modes, which you are seeing here, can just appear from a white noise. That's all. 1 year negative, next year positive, and negative and positive. The probability is 67%. You can just generate from the random noise. That's all, random variables. So then when I was doing that, actually that time we also did something in the in-house analysis. I think I will not go to details of that analysis. What basically is the details of that is just maybe 5-10 minutes more, right? It should be okay. 10 minutes. Like 4 o'clock. So what you do is that you take a particular grid over Indian region, and then you have a daily rainfall, right? A particular year. So you can create a PDF of that. And there are several zero rainfall years, zero rainfall days, right? So if you remove the zero rainfall days, then now there is a PDF, right? So that PDF kind of in a log distribution is somewhat looks like this. If you include the zero rainfall, that is very, very large, depending on the region, depending on the whatever, right? So this is kind of uniform. I mean, most of the cases, most of the regions over Indian region. All right. So just independent of these people, what they are trying to do, because for their analysis does not have intensity of rainfall. There's a pure statistic, just the number, frequencies. Okay, there is no value of rainfall. So for the Indian region, now I try to fit this particular distribution using some statistics. So take up, but do a fit, get the coefficients, right? So then you get coefficient at every grid point, every year, right? So you get a mean coefficient and you get a standard deviation of coefficient. So what is basically saying is that the mean coefficient will give the mean picture, the standard deviation of the coefficient will give you the internal variation, right? So now take these two, assume that they are Gaussian, or use that mean and the standard deviation, create a Gaussian distribution, random distribution, pick up from the random distribution different random variables or the values 1,000 times, basically 1,000 different rainfall you have. They are going to reconstruct the rainfall, 1,000 different rainfall which you have, and create the rainfall time series they gave you. Just that says that the mean is consistent with what we observe, but not its internal variation. That's the baseline here. The mean is, so basically what I'm saying, the mean of coefficient one, all of the coefficient and standard deviation, and there are few others. And this is the mean of the rainfall synthetic data, which kind of looks very similar to what we observe. And this is internal standard deviation of the synthetic rainfall, all right? So if you take these two, and if you take this 1,000 years of rainfall here, anomaly, this is here, okay? And this rainfall anomaly, now if you do a power spectrum density, you get a large peak again at 2 to 4 year time scale. So again, what I'm trying to say is that you can again create this biennial signal, right? I mean, biennial signal, therefore, need not be physically connected, at least it says, right? You're just picking up from the random variables, create a time series, you create a biennial signal, which is somewhat like an observation, without the fact that there is no ENSO signal. But now you can introduce that ENSO signal but this is by forcing, by just add that particular frequency there in the time series. This is nothing. Okay, so I'm just saying that it can be introduced, but these are all random. Right? These are all randoms. Okay, so still it is not over. The story is not over. So basically, what I'm trying to say is that several atmospheric parameters in the troposphere show largely better than the Gaussian factor. The recap everything. TBO can be generated purely from a random ones. At least two different value statistics shows that. However, the large scale aspect of the TBO cannot be ignored. So what we are trying to say is that at every grid point, every location, if there is some random number, right? They must be independent of each other. Then how come this is the signal of TPO at the large scale, rainfall and the winds? How come it is so coherent, spatially coherent, right? As well as Indian and Australian rainfall are in phase. Indian rainfall to Australian rainfall and the back to back and forth. So even from the one season to another season, it cannot be only random, because purely random, there will be anything else will be uncorrelated from one season to another season, one location to another season. Therefore, we must be missing something. Now look at our Indian region. I think I'll skip that. Okay, so this is the very similar steps. Then what I try to do is that take the synthetic data, calculate the frequency of biennial oscillation, biennial peak. Okay, according to the definition of biennial peak. And this is for IS. So this is about, I say, the 67% of the years are biennial, right? However, if you take from the synthetic data, pick up the biennial time period, its variance, fraction of variance compared to the total time series is only about 40%. All right. And for the ISMR, it is about 60%, more than 60%. What I'm trying to say is that synthetic data, although has a biennial signal, its variance explained by that particular signal of the total is much bigger than in the real data set. Okay, so you can get statistics, but you won't get the variance. You get the frequency, but not get the variance. That's the point here. So there must be some physical modality, right? So if you do it independently, IMF of precipitation over PUR together, you get that's a kind of coherence over this one. And not just that, if you take the total PUR and total ISMR, there is some sort of a relationship here. But if you take the biennial mode, the relationship to some extent, at least there is an increase here. So whatever is the rainfall and pure are more strongly coupled at biennial time scale. So what I'm trying to prove is that most likely they are, even if a random noise can generate tropical biennial oscillation, it further gets enhanced by coupled interaction between the atmosphere and ocean. Without that, the observed tropical biennial oscillation is not possible to get, which is so coherent in space and time. So it may be statistically generated, but there must be a physical mode that kind of enhances it so that it increases the variance as well as it makes it coherent in space. Okay, I think that's the last slide. Yeah, thank you.
Any other questions? A nice review of the whole subject. Anybody has? Yeah, my problem is I always thought of white noise has no preferred frequency by definition. So why is biennial coming there?
So that's the thing. So it
It's
is
not red noise, it's white noise, right? So white noise has no preferred frequency. But
so actually no. Whatever this is a Gaussian white noise. What is that? There is a mean, and there is a standard.
no, if you give me a completely white noise signal and I do a spectral analysis, I will get no preferred frequency. Am I right?
Yeah.
Yeah.
So but that's
So
the uniform distribution. That's for uniform distribution. But this is for the Gaussian distribution. So for the Gaussian distribution, if there is a mean, right, and then I pick up one value which may be less than the mean, I cannot pick up or in randomly there cannot be successive several values which is less than the mean, because then the mean itself will shift. So by statistics, if one value is less than the mean, other value is most likely to be higher than the mean, and the next value again less than the mean, and to some extent, a few times maybe it is less.
But why should they occur in alternate years?
That's the thing. It is exactly not alternate, but it's only 67% of the years. That's the thing it is showing. It's only 67% of the years they alternate. So this is the one really purely from the Gaussian distribution. This particular thing. At 67% of the time, the successive values are changing their sign. The mean is 0. So 1 year is less than 0, or one value is less than 0. Next value is more than 0. This particular figure is exact just from one time series.
Yeah, if that's the case, then you should use that information for forecasting, right? If that's what you're saying, forget all the physics. Knowing that last year monsoon was above normal, I would say below normal, and this year monsoon above normal, purely from that kind of argument. Can that be added to the forecast?
I'm not very sure because it is not regular, no? So I'm not very sure of that, because since this time series, if you go back, even the biennial part is not regular. So I'm not very sure of that. So look at this. Even this is the first move. The first problem is that what is the definition of the biennial move? Because different techniques will give you different thing. And then even this is orange line is the biennial mode to some extent. They are really not every year that doesn't become possible.
Let me give you a crude idea. You got this nice, I'm a one, I fit some function to it, and to my ENSO base program, I add to it, improve my forecast.
Ideally,
Right?
I think that
I just force it extra. That's what in a way Iyengar did.
Yeah.
Iyengar's IMR1, his prediction was based on a neural model.
Yeah.
And so I think he picked a random number and chose a value.
Yeah.
It was right for 10 years. And then,
right.
yeah. So question is, can anybody, given this thing, can they predict the next year more accurately than anybody else?
Yeah,
Yeah, that's the issue. Because to me, if you look at this figure, it's amazing. All the extreme here, it reproduces correctly, right?
Yeah.
It's truly remarkable.
Yes.
I don't know any extreme year in which it is not showing the right sign. Right? Yeah. Absolutely.
Yeah.
So it's so it should be possible to use the information somehow. In addition to physics, add a little bit of
statistics there.
Anybody else?
Is there any question online also?
Yeah,
Okay.
Arindam, can you hear me? Hello?
Yeah.
Yes. Hello?
Arindam, am I audible? Hello?
Yes, you are audible, yes.
Yeah, I just want to ask one query from this slide only, slide number 12. Yeah. So for this ISMR, 50% of the variability comes from ENSO, right? But we don't see any significant peak in the power spectra. Like, I just want to understand why it is not coming like that.
50% of the ISMR variance is this one. No. 50% is not, because even if you go by the ENSO and rainfall correlation, it is about 0.5, say. So square
Yeah.
of 0.5 will be 0.25. So it's basically 25%. It's not 50%. So 25 to 30% maximum. Okay,
Yeah,
so it
but
won't be 50%.
there is no significant peak in like 3 to 7 year band. Peak
Yeah,
is there at 5, but it is not significant, right?
right. Not significant. No, I cannot say it is significant or not, but it is much less than the biennial peak. But please remember that AMs also have a biennial peak, right? So if
Yeah,
you
that
add
is, yeah.
that,
Mm.
isn't it? So it is not only the 5 to 7 year peak is ENSO. ENSO also has a biennial signal. So when that gets coupled to Indian monsoon, so that will give you that explain more variance, right?
Okay, like there are many studies which say that like there is a known spectral dip in that ENSO band that is like specifically 3 to 7 year band. So uh,
Yeah. So that's what I'm saying. So only the 3 to 7 year band cannot be on the ENSO band, right? ENSO also has a signal spectrum or the power at that two to
yeah,
4 years, right? So and
yes,
ISMR is also coupled to that. This is well known that biennial spectra of ENSO.
okay. But when you create that synthetic ISMR, when you are adding that
Uh,
ENSO signal, you are getting a significant ENSO peak there.
that's because I've deliberately added the ENSO 4 to 5. I think I've added a 5 year time scale there. So that is nothing. That is just to show that you can add some forcing from outside. That's all.
Okay. And
That was just generated.
okay, one more question I want to ask, like for in year 1997, there is increased rainfall over Western Ghat and decreased over Central India.
Yeah.
So there are studies like by Mishra et al. 2012 which state that there are two patterns of ISMR. Like first one state that it is connected with ENSO, and second one state there is a that bipolar character like here in 97, yes,
Yeah.
in GPCP. So there is like positive over Western Ghat and negative over Central India sort of. So
Right.
is there any like specific physical mechanism which can explain this? Like for 97, there was IOD that is also there.
Yeah, that's the
But
thing.
in
So
general also, yeah, in general, is there any specific mechanism which can explain that contrast between peninsular India and this like Central India domain?
I think actually Central India and Eastern India usually disconnected or the opposite polarity during ENSO time. But from this figure, I am not what is called
No, not
demanding
from.
is that,
I'm using this just as a reference. Like
uh,
if we calculate like two dominant mode, like two EOFs, EOF1 and EOF2, we say that EOF1 is governed by ENSO, and EOF2 there is no physical mechanism. It is just a like statistical signal we are getting. So that signal matches very well with this 97 GPCP anomalies.
no,
So
you
can
have
we get
to. Yeah, UF2 actually depends on that, what region, what this one, unfortunately. But UF2, if you take only over Indian region, actually is
yeah
connected to the Indian Ocean. You can look at, there is a paper by Mike
yeah
Wallace, and
yeah
they show that UF2 is kind of connected to the Indian Ocean. But anyway, there's a definition dependent.
okay okay thank you.
Okay, thank you. Anything else? Ravi, okay.
Yeah.
Hello?
Hi, Arindam.
Hi,
Hi,
Ravi.
can you hear
Hi.
me?
Yes, I can hear.
Yeah. So interesting analysis. Uh, I mean, okay, I have to only one comment that is basically, both Australian monsoon and Indian monsoon are affected by a common event, which is the El Nino. So are we
Right.
seeing two physical independent things, or it's a kind of a response to the same kind of forcing that we are getting?
Actually, you are very right. I made that figure and I have not shown it. That particular scatter, right? Wherever I have shown you that Indian or Australian monsoon, isn't it? most of this, yeah. So this particular case, most of the positive rainfall where both of them are positive are related to La Nina. Actually, you are very right. So this again, but goes to the biennial signal of the ENSO also. So I don't know where to distinguish what. So we don't know. So, but you are right. It most probably it will be connected through ENSO.
Okay. My other one is,
Yeah.
like there's a paper by Meal, I think it's quite old, where he kind of invokes soil moisture feedbacks to kind
Yeah.
of get this TBO. This I think goes back to the 90s. So you think that is the actual mechanism, or there's some other mechanism which is kind of coming for this TBO, so to speak, or the Indian Australian TBO?
Yeah, the soil moisture, no?
Yeah, soil
Actually,
moisture feedback. I think.
we have done simulation in the lab. Okay, that we have done simulation with that with the even with climatological SST. We got a biennial signal even with climatological SST. I have not shown you. There is no time.
Okay.
So even with climatological SST, so there is a possibility. There will not this one. I mean, rule it. I mean, Shikhar and Sujatra, the boy and Tananga, all of them have done that. You are right, Ravi. Again,
Okay. No. Thanks, Arindam.
thank you. Anything else?
Okay.
Okay, thank you. Let's close this. Okay.
Yeah. Thank you, Arindam. So I'll give you a brief summary of what happened in the last 2 weeks. Uh, yeah. So remember when we met 2 weeks back, we had a doubt whether, although onset occurred in Kerala on time, very close time, we thought it would not progress very well, but it did. As a matter of fact, the last 15 days, the monsoon has gone exactly according to what is there in the textbook. Okay. Actually, I want you to notice one thing which is very curious. On 1st June, they have drawn this line along the state of Kerala. To me, it's very peculiar. Okay. This was about their data, Kerala rainfall data, and it had a lot in Kerala on that day. But to me, when they are drawing their lines somewhat smoothly across, this should also have gone this way, but they have done it exactly over Kerala because Tamil Nadu has no rain during the monsoon season. Other than that, they are all going. I'm still not clear. Somebody should tell me, is there any basis for drawing this line? I don't know. Here I can understand. There are a lot of data here they might try to. But even now, I think they're just drawing a line, connecting that and that. But the fact is that it has gone along exactly as per the climatology up to, and actually a little bit ahead. If you look at the 12th June here, it is about 1 week ahead of the climatology. So it's going quite well, but we don't know what's going to happen next. So if you look at the till yesterday, it was only 1% from the normal, and all India. Of course, you can see North India doing very badly, East India doing badly. Central India is quite close to normal, interestingly. Although the monsoon has only come up to this, that's enough to give Central India sufficient rainfall. Of course, South India doesn't know, because a lot of rain has occurred in the last 10 days. Now, here is the all India monsoon rainfall up to 11 June, and so today also I saw it is somewhat lower than this. Okay, so there's already a hint of monsoon slowing down. Okay, so the next 1 week is going to be somewhat critical for June rainfall, because although we had a good start, went almost normal till June 10th, but things are indicating that things are going down. Now let's look at the Somali jet. This is from Windy. Shows a clear, strong Somali jet. This is a little older, 2 days ago, all around this region. So as the monsoon progresses, Somali jet also is showing clear signature. And I'll show you some data from Biennial also. Yeah, this is the answer Biennial data. This is June 1st, this is June 9th. Okay. See how well the jet has moved all the way to somewhere around 18 now. Okay. So the rainfall and the jet are as expected going together. Now this is this morning's windy picture at 12 o'clock, and this to me is an indication of bad news. If the monsoon is progressing well, you shouldn't see this picture. The clouds are there only over Bay of Bengal, there's nothing over India, almost. Okay, but be a little careful, although I like to look at windy often. But there's a strong downward cycle in the monsoon. Okay, so I will look at tonight and see that by chance something develops here. But so far there's no hint of any I saw nothing is developing here. So definitely that is today's rainfall, which is about tomorrow, will be below normal definitely. Okay, from this indication. So there's a hint of something trying to suppress rainfall. This is the water vapor from satellite data. And the reason why I think we are concerned about is that as the water vapor comes from here across to India, if this layer, if this region comes to, no problem. But if this one, which is very low, water vapor comes, then we would have a slowdown on the monsoon. Okay, so we have to watch. I'll show you next week how this is evolving. So it will be interesting to see which parcel is hitting India. As a matter of fact, I always felt that although the tradition in meteorology has been oil framework, that is field description of the monsoon, because convenient, all of us do that. But the best way to understand monsoon is Lagrangian. You follow the parcel. Okay, but it is more complicated. It's more messy. So I forgot. Next week I'll show you one paper published by first author in IIT Bhubaneswar, I think, and very impressive piece of work. He has followed every parcel, and thereby he's able to explain rainfall. Where did the water vapor come from? It come from Arabian Sea, Southern Indian Ocean, Bay of Bengal. And this issue has been discussed the last 60 years, but till today we didn't have good data. So now with reanalysis and so many other sources of data, we can answer the question more precisely, and we will understand the monsoon better than the typical field description that we do, which doesn't tell you where did the water will come from. Okay, so this will follow next week and see what happens. Now this is again answer reanalysis. Again, I'm showing you on June 1st, water vapor was right here over Kerala and Sri Lanka. By June 9th, it has come up to this region. Okay? And note that during all this period, East Asia obviously has an earlier onset than India. It has not more water vapor. Okay? Now this will switch. As the Indian monsoon strengthens in July, things will change. Okay? Right now, you're still on the onset phase. Okay, this is the core monsoon zone, which is not all India. And notice already a warning is there. In the core monsoon zone, already there's a clear indication of monsoon being below normal. Okay? So you'll see the next few days, things not going to go on this path. That's why I felt there should be a theory for the onset of the core monsoon zone. And Arindam has done some work, but not published it, right? So it's worth pursuing. Somebody should be able to say, like I say for Kerala, for core monsoon zone, what the onset date and how it will progress. Okay? I can tell you, for those who live in North India, people in Kerala are lucky June 1st it will come. We live in Delhi or Kanpur, I lived in both places. Whole of June, we are struggling to wait for when the rain will come. Because it's very hot and we are desperate. And our travel with train from Delhi, Kanpur to here, it's a nightmare, okay? So somebody should make a better forecast as to how the core monsoon zone will evolve in time. Okay. Now let's look at El Nino. It's rapidly falling. I like this somewhat sympathetic looking figure. Okay, from last year when it rose rapidly from January 23 to December 24, and then it's fallen. So it's going to go on this clearly. So it's going to come down. It's not yet a La Nina, but it's going to happen in the next few weeks. This is IOD. IOD shows no signal right now. It's close to zero. So unless something happens and things change, so far there's no hint of IOD playing a role. Okay, let's look at the forecast that IMD made in the first week of June. I would say, except for one day, the forecast is green, is well below that. They got it right most of the time. Okay? So this is the first week after onset. They got that more or less right, except 1 or 2 days. Then this week, I would say they're pretty good. But now is the important turning point. They are showing a slight decline the next 3 days. Then I'll show the next picture, they are showing an increase. Okay. So they are saying it's somewhat weak for 4 or 5 days, then you pick up, that's okay. That's a typical monsoon behavior. But other models are not showing that. That's what I want to argue. So this is what IMD is indicating based on CFS-V2 that yes, will be next 1 week will be below normal, and then it will pick up by 19 June. Now that's a big question. If it picks up, then the June rainfall will be close to normal. If it does not, it will be below normal. Let's see what the other models are saying. Now this is interestingly, this is also the same model used by India Met Department, but by the American original model. There's a small difference of that. It is saying up to June 25th, the next 2 weeks, rainfall won't go beyond this. Okay. And what I'm impressed by is forward agreement between 2 different weather centers. What I say, there's no way we'll go beyond around 20 knots. But IMD is saying not to go up. So let's see next week who is going to come out right. Now this is IMD prediction. Okay. IMD is showing that this week rainfall has not gone up this far so far. Today is 12. I don't see anything here. So they are predicting rain going up somewhere here and no rain here. That's okay. Next week they're also agreeing that there will be no progress. Most of no normal. So after this, up to I would say 20th, everybody agrees. Then the week after is where the problem comes. The week after, IMD is saying all India is 20% above normal. The week after, 18% above normal, 78% above normal. This is where there's a difference. And if you recall the history we had for the last 10 years, usually the third and the fourth week forecast is not very accurate. So let's see who comes out right in the third and the fourth week. The coming week, everybody agrees will be below normal. Now, here's one more prediction from ECW showing the spatial structure. Clearly, it's showing up to 24. Things are not going for beyond it. And this is pretty large deviation. Okay, remember this is weekly average. They are saying something like 15 millimeters below normal in a week's rainfall, which is not negligible. And the interesting part about which I will discuss next week, that there's a dipole structure here. East Asia is doing better, not East Asia, sorry, West Pacific is doing better, East Asia is here. So this structure, let us see whether is reproduced in observation next week. Okay, now from the NOAA website, I saw this MGO discussion. So normally people believe that during a La Nina year, MGO is not very strong. Right? But remember, La Nina has not yet come. La Nina is very come. It's been announced, but it's not there. So MGO is playing a role. So according to NOAA website, this is a prediction based on June 10th for the next 15 days. They are saying positive all are normally in the next 15 days for India. So if this is right, this is also forecast, not GCM based, but some kind of extrapolation. If this comes out right, then NGO is right here, it is going to decrease the rainfall, then both GFS and ECM will be right, and IMD may go wrong somewhere here, 15 days from now. So MGO behavior is going to have an impact. Now, here is an example given the same website, how the OLR normally is there, average over 10 days. Okay, so what I will show you, the onset week, the things are very strong here, that's why we have a good onset, it went on quite well. Okay, the week after the onset, that is the current week, this got about weekend and something big is happening here. This is MGO signal. This is going to move. I'll show you next week. This will move over here, I think, if they are right. Okay. So we'll see whether that will emerge or not. And now also I want you to look at what's happening. We saw last week or 2 weeks back there was a very warm anomaly over Indian region. Okay. Now, this is the change in SST from 1st to 29, 1 month's time, last 1 month approximately. This is all fully. Okay. So that's not good news, because if you believe in the role water vapor plays, if this region cools, then we don't get enough water vapor over India. Okay. So that is already hint that whatever good things happen are going to slow down. But of course, if El Nino develops, La Nina develops rapidly, things may change. Okay, so I want to end with the last slide based on what Mohit, the question he asked. So he said 1983 was an interesting year in which in May, Dino 3.4 was 1. Okay, this year it was around 0.5, 0.6. And it continued to be above 0.5 in June. Right? Now we have gone to 0.3 or so. And then rapidly declined in July and August and September. Right? So what happened to the rainfall? The rainfall in 83 was pretty high, close to the flood year. Okay? See the ultimately would be in June, July, and August, September. Okay? June, July, La Nina had not yet really established itself. So the rainfall was not below normal, but normal. But once the La Nina became strong, suddenly the second part of the monsoon was 120 millimeters above the coast. Okay? So that's what you should expect this year. Even if the monsoon weakens in the next few weeks, July will probably be normal, and August, September will really make up. Okay? So if you look at climatology, these two should be approximately equal. Normally this is 450 and 430 typically, the 2 halves of the monsoon. Okay? But in a year where La Nina is developing and is going to go full strength, the second half will play much more important role. That's the goal of 83. But I'll look at all the other years and show you next time how they behave. Because 83 was very special. But I recall that many models couldn't get 83 right. Because to get 83 monsoon right, your model SST has to show this structure. If they went like this, they got it wrong. Okay? So this was an interesting phase. I remember many models did not capture 83 correctly. The way the monsoon came, but it became strong after July 31st. Okay. Yeah. So I want to point out next week, Dr. Arindam, one of our students from COS, who is in fourth Paradigm Institute, has agreed to give a talk. He runs a CFS V2 model in a very powerful computer, and he has done multiple cases, and he'll come and tell us what his model is showing for the coming year. Okay. So are there any questions?
Particularly, our line of then become weaker and weaker. Now people are doing a much stronger line right from September, like a couple of months ago.
Yeah.
Now they are predicting a much weaker line.
Really?
Yes.
Oh, which one you're talking about?
CFS V2 and all models, I think most of the models.
Compared to May.
Yeah, compared to even April.
Huh?
April.
Okay, then next I'll show. Yeah, coming April to June.
Yeah.
You're saying difference. No, I don't think. Well, I'll see. I'll go to because they keep reporting. Yeah. So they say La Nina is weaker.
Yeah, they said that now La Nina is going to be weaker this summer.
Okay.
So I'm not very sure when they will La Nina. The way they are going.
Yeah, that's it. That's interesting because when I checked it yesterday, but somehow I didn't. Maybe it was not good for. Yeah, IRA website. Right. So we get
Or is it long? This one. I have a time series. I'll send it to you. I think I also made a time series. Like I share.
Okay.
So
Yeah.
There's a clear difference. Very clear.
Between April and June. That's interesting. Yeah. Okay. Thank you.
Average more the